was indeed a serious one, and it was first attacked in Great Britain by Neville Maskelyne, 1732 to 1811, who was Astronomer Royal. If we know the volume of the Earth and its density, referred to some standard as water, air, or iron, it is, of course, easy to determine its mass. But the determination of its density is no less a problem than the determination of its mass directly. It is possible, of course, to compute the relative amount of water, but this gives only a small amount of the mere surface of the Earth. We can descend in mine shafts a mile or more and investigate the nature of the material, but this again affords no clue to the thousands of feet of materials below, so that an estimate of the average density based on such data cannot be considered at all trustworthy. Newton, taking into consideration the various elements of the Earth, estimated its density at between 5 and 6 times that of water. Maskelyne, however, bearing in mind the phenomenon of the deflection of the plumb line observed by Bouguer and Le Condamine in their expedition to measure an arc of latitude in Peru, a phenomenon caused by the attraction of the mountain Chimborazo, selected the narrow ridge of Schehallien in Perthshire, and found that the attraction of the mountain caused a deflection of about 12 seconds on each side of the ridge. This attraction of the mountain, as compared with the attraction of the Earth on the plumb bob, enabled a value for the density of the Earth of about 4.5 times that of water to be obtained. It remained for the famous Cavendish experiment, carried out by Henry Cavendish, 1731 to 1810, to substitute for the mountain a pair of heavy balls. This gave a value for the density of the Earth of 5.5 times that of water, a value confirmed by numerous repetitions of Cavendish's classical experiment. Expressed in pounds, the mass of the Earth is a little more than 13 billion, a figure that the human mind utterly fails to grasp. There must have been a time when the Earth contained much more heat than at present. The sun is not supplying heat enough to make good the losses sustained by the globe. These losses must have been taking place over a period of countless years. One is forced to believe that not only once was our Earth much hotter than at present, but that its temperature was a red heat. Going back still further, the now solid globe must have been actually a molten mass. Being a molten mass, it is not difficult to realize that it readily assumed a globular form on its journey through space. A falling drop of rain is a globe. A drop of oil suspended in a liquid with which it does not mix has a spherical shape. Therefore, if a mass of material as large as the Earth were so soft that its individual particles obeyed the forces of attraction exerted by each part of the mass on all the other parts, it is quite obvious that it would assume a globular shape, especially under the influence of motion. If this great sphere were caused to rotate around its axis like a ball of clay on a potter's wheel, any lack of true sphericity would not only be overcome, but there would be a tendency for the molten body to bulge at the equator and flatten down at the poles, forming an oblate spheroid, such as by actual measurement the Earth is found to be. Indeed, not only is the Earth an oblate spheroid, but most of the planets which can be measured have become flattened at the poles for the same reason. In connection with the spherical shape of the Earth, mention should be made of a recent theory which seeks to demonstrate that the shape of the Earth is being transformed into a polyhedral form, or more exactly, that there is a tendency in the direction of its assuming the figure of a regular tetrahedron or four-sided figure, each of whose faces is triangular. This is manifested by the lithosphere or solid portion of the Earth. The water is massed on the faces of such a tetrahedron, the force of gravity acting most powerfully at the center of each of the four surfaces. The tetrahedron hypothesis assumes that a more or less solid crust was formed when the Earth was still perhaps in an approximately spheroidal form. As contraction occurred in the interior, the external shell proved too large. Hence, a different form has to be assumed, which it is asserted would be the tetrahedral. On each of the faces of such a tetrahedron, one of the four oceans would lie, the Arctic Ocean being assumed as the fourth for the region about the North Pole. The continents would correspond with North and South America, Euro-Africa, Asia, Australia, and Antarctica. This hypothesis is borne out in many respects by geological and other considerations. First advanced in the 70s of the 19th century by Lothian Green, the hypothesis has been put forward in recent years with further developments and attempts at its proof, so that it is considered as a tenable and possible explanation, though its absolute soundness has not been demonstrated. Recognizing and proving the spherical shape of the Earth by no means explains the apparent motion of the sun, moon, and stars as regards the planet. As the nature of the solar system was developed by Copernicus and Newton, people were compelled to recognize that the Earth revolved around the sun, and furthermore, that it rotated daily about its axis. These motions are necessary to explain various phenomena. For example, when a body moves in a circle, a force is needed to act on it, pulling toward the center proportionally to the square of the rate of spin, and proportionally to the distance. Every pound of mass in the moon would need a pull equal to about the weight of 3 ounces to keep it in a circle which it traveled around once in 24 hours. Every pound in the sun would need a pull about 3/4 of a hundredweight. The nearest fixed star would need a pull on every pound of about 9,000 tons. One cannot imagine that the Earth could exert such forces, and so are obliged to think that the Earth is revolving and not the sky. Final proof of the rotation of the Earth was furnished in the middle of the last century by Foucault. His experiments were constantly repeated in physical laboratories and experimental lectures. From the dome of the Pantheon in Paris, he suspended a heavy ball by a fine cord and caused it to swing in a single plane. The path of the ball across the floor could be traced, and it was found that after it had been in vibration for some time, it was swinging in a different direction from that in which it had started. The reason was that the floor had revolved under the ball with the rotation of the Earth. The daily rotation of the Earth on its axis and its yearly rotation about the sun supply us with our means of measuring time. According to Professor Poynting, quote, "The Earth is a clock. The line to the sun is the finger, and the sky is the face. But the Earth is not a regular timekeeper. Our 24-hour day is only the average between successive noons or times when the sun is due south. If compared with a good clock, the sun is in parts of the year too soon and in other parts too late, sometimes as much as 1/4 of an hour. This cannot be due to change in the Earth's rate of spin, for to change a spin there must be either a force acting at one side of the center of gravity or a change of shape. The forces on the Earth exerted by the sun and moon act almost exactly through the center of gravity, and so affect the rate of spin hardly at all. The Earth does not change its shape sufficiently to account for the variation in the solar day. The variation in the solar day is due partly to the inclination of the Earth's axis to the plane in which it moves around the sun, partly to variation of the Earth's motion around the sun at different times of the year. The fixed stars keep good time, getting round in about 4 minutes less than 24 hours. By them, clocks are rated. Their day is the true time of one rotation of the Earth." Unquote. End of section 18. Section 19 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Nagami. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy. Chapter 13. The Earth, Part 2. Among the movements of the Earth, there is one that is so minute as to be of peculiar interest to the astronomer. It is a small displacement or wobbling of the axis of the Earth, or theoretical pole. This pole shifts its place through a circle of some few yards in diameter in the course of a period of somewhat over a year, and as a result there is a variation of latitude on the Earth's surface. This was discovered first in 1884 and 1885 by Dr. Küstner at Berlin. and after observations made at various stations by members of the International Geodetic Association in 1888, it was found that this synchronous variation was occurring in a periodic manner at a number of stations. The general nature of the occurrence was defined by Professor S. C. Chandler in 1891, who stated that the pole of the Earth might be supposed to describe a circle with a radius of 30 feet in a period of 14 months. One reason assigned for this phenomenon is a change in the distribution of mass due to the temporary occurrence of heavy falls of snow or rain limited to one continent, or to the transportation of great bodies of water and air from place to place by atmospheric or sea currents, so that the globe is made slightly lopsided and temporarily to forsake its normal axis. Also, it has been supposed that the Earth is not absolutely rigid. As a quasi-plastic mass, it would yield to certain strains, which tend to protract the time of circulation of the displaced pole. In fact, in all consideration of the various phenomena of gravitation and tides, we have to recognize that in practice the astronomer of today is not dealing with the theoretically rigid body of Newton and the earlier mathematicians. One of the important conditions of the rotation of the Earth is that it moves around an axis which is not vertical, but which is inclined toward the plane of its orbit. Dolmage, in his volume Astronomy of Today, tells us that, quote, if the axis of the Earth stood straight up, so to speak, while the Earth revolved in its orbit, the Sun would plainly keep always on a level with the equator. This is equivalent to stating that in such circumstances, a person at the equator would see it rise every morning exactly in the east, pass through the zenith, that is the point directly overhead of him at midday, and set in the evening, due in the west. As this would go on unchangingly at the equator every day throughout the year, it should be clear that at any particular place upon the Earth, the Sun would, in these conditions, always be seen to move in an unvarying manner across the sky at a certain altitude, depending upon the latitude of the place. Thus, the more north one went upon the Earth's surface, the more southerly in the sky would the Sun's path lie, while at the North Pole itself, the Sun would always run round and round the horizon. Similarly, the more south one went from the equator, the more northerly would the path of the Sun lie, while at the South Pole it would be seen to skirt the horizon in the same manner as at the North Pole. The result of such an arrangement would be that each place upon the Earth would always have one unvarying climate, in which case there would not exist any of those beneficial changes of season to which we owe so much. The changes of season which we fortunately experience are due, however, to the fact that the Sun does not appear to move across the sky each day at one unvarying altitude, but is continually altering the position of its path, so that at one period of the year it passes across the sky low down, while at the other it moves high up across the heavens and is above the horizon for a much longer time. Actually, the Sun seems little by little to creep up the sky during one half of the year, namely from midwinter to midsummer, and then just as gradually to slip down it again during the other half, namely from midsummer to midwinter. It will therefore be clear that every region of the Earth is much more thoroughly warmed during one portion of the year than during another, that is, when the Sun's path is high in the heavens than when it is low down. Once more, we find appearances exactly the contrary from the truth. The Earth is, in this case, the real cause of the deception, just as it was in the other cases. The Sun does not actually creep slowly up the sky and then slowly dip down it again, but owing to the Earth's axis being set aslant, different regions of the Earth's surface are presented to the Sun at different times. Thus, in one portion of its orbit, the northerly regions of the Earth are presented to the Sun, and in the other portion, the southerly. It follows, of course, from this, that when it is summer in the northern hemisphere, it is winter in the southern and vice versa. The fact that in consequence of this slant of the Earth's axis, the sun is for part of the year on the north side of the equator and part of the year on the south side leads to a very peculiar result. The path of the moon around the Earth is nearly on the same plane with the Earth's path around the sun. The moon, therefore, always keeps to the same regions of the sky as the sun. The slant of the Earth's axis thus regularly displaces the position of both the sun and the moon to the north and south sides of the equator respectively in the manner we have been describing. Were the Earth, however, a perfect sphere, such change of position would not produce any effect. At present, the north pole of the heavens is quite close to a bright star in the tail of the constellation of the Little Bear, which is consequently known as the pole star, but in early Greek times it was at least 10 times as far away from this star as it is now. After some 12,000 years, the pole will point to the constellation of Lyra and Vega. The most brilliant star in that constellation will then be considered as the pole star. This slow twisting of the Earth is technically known as precession, or the precession of the equinoxes. We have seen that the orbit of the Earth is an ellipse and that the sun is situated at what is called the focus, a point not in the middle of the ellipse, but rather toward one of its ends. Therefore, during the course of the year, the distance of the Earth from the sun varies. The sun, in consequence of this, is about 3 million miles nearer to us in our northern winter than it is in our northern summer, a statement which sounds somewhat paradoxical. This variation in distance, large as it appears in figures, cannot, however, be productive of much alteration in the amount of solar heat which we receive, for during the first week in January, when the distance is least, the sun only looks about 1/18 broader than at the commencement of July, when the distance is greatest. The great disparity in temperature between winter and summer depends, as we have seen, upon causes of quite another kind, and varies between such wide limits that the effects of this slight alteration in the distance of the sun from the Earth may be neglected for practical purposes." End quote. The most striking effect of gravitation in its universal aspect is seen on the Earth in the case of the tides, which are due to the attraction of the moon on the Earth and especially on the waters of its ocean. While the ancients could not explain the cause of the daily change in the tides, the phenomenon was obvious to all mariners or those dwelling by the sea or even on great rivers. The connection of the moon with this phenomenon, it is claimed, was understood as early as 1000 BC by the Chinese, for at full and new moon exceptionally high tides were observed, and the name of spring tides was applied as contrasted with the minimum high water which was observed at the neap tides at the second and fourth quarters of the moon. Not only the Chinese, but the Greeks and Romans noticed this same phenomenon, and Julius Caesar in his commentaries tells us that when he was embarking his troops for Britain, the tide was high because the moon was full, while both Pliny and Aristotle connect the time of high water with the age of the moon. The connection between the moon and the tide was thus early established and practically applied by navigators, who were quick to realize the nature of the phenomenon, even though they and the astronomers were unable to present any satisfactory explanation. A general explanation of the tides as due to the disturbing action of the moon and sun, especially the former, was put forward by Newton. Newton's explanation, as described by Berry in his short history of astronomy, was as follows, quote, "If the earth be regarded as made of a solid spherical nucleus covered by the ocean, then the moon attracts different parts unequally, and in particular the attraction measured by the acceleration produced on the water nearest to the moon is greater than that on the solid earth, and that on the water farthest from the moon is less. Consequently, the water moves on the surface of the earth, the general character of the motion being the same as if the portion of the ocean on the side toward the moon were attracted, and that on the opposite side repelled. Owing to the rotation of the earth and the moon's motion, the moon returns to nearly the same position with respect to any place on the earth in a period which exceeds a day, by, on the average, about 50 minutes, and consequently Newton's argument showed that low tides or high tides due to the moon would follow one another at any given place at intervals equal to about half this period, or in other words, that two tides would in general occur daily, but that on each day any particular phase of the tides would occur on the average about 50 minutes later than on the preceding day, a result agreeing with the observation. Similar but smaller tides were shown by the same argument to arise from the action of the sun, and the actual tide to be due to the combination of the two. It was shown that at new and full moon, the lunar and solar tides would be added together, whereas at the half moon they would tend to counteract one another, so that the observed fact of greater tides every fortnight received an explanation. A number of other peculiarities of the tides were also shown to result from the same principles." End quote. From Newton's time to the present, the tides have supplied material for astronomical and mathematical research, so that through the efforts of many astronomers and other scientists, their theory and occurrence are now well understood, and the various governments make ample provision through hydrographic offices and otherwise to provide such information for mariners. In the theoretical discussion in modern times, one name stands out prominently, that of Sir George H. Darwin of England, whose researches on the tides of the earth have developed to a point where they have a most important bearing on cosmical theory. It is desirable here to outline the chief features of tides in their everyday occurrence. The term flood tide is applied to the rising water which reaches high water mark at the moment when the tide is highest, while in falling the tide is said to ebb until low water or the lowest mark is reached. Near the times of new and full moon occur the spring tides, which are the highest tides of the month, as distinguished from the neap tides, which are the smallest, occurring when the moon is in quadrature. The relative heights of spring and neap tides being about as 7 to 4. At the time of spring tides, the interval between the corresponding tides of successive days is less than the average value of 24 hours and 51 minutes, and the tides are said to prime, the interval amounting to about 24 hours and 38 minutes, while at neap tides the interval increases to 25 hours and 6 minutes, and then the tides are said to lag. The highest tides of all occur when the new or full moon at the time the moon is in perigee, especially as this takes place about January 1st, when the earth is nearest to the sun. Not only are the tides interesting for their relation to navigation, but on account of their intimate connection with the motion of the earth. The daily movement of the tides is a drag on the energy of our planet and is acting to cut down its speed of rotation. If the speed of rotation of the earth diminishes, it is obvious that our day is being lengthened, that today is longer than yesterday, and that tomorrow will be longer than today, even though these increases are all but inappreciable in the time that the human mind can fathom. Sir Robert Ball, in his Story of the Heavens, summarizes the variation wrought by the tides in the following paragraph, quote, "Let us take a glance back into the profound depths of times past and see what the tides have to tell us. If the present order of things has lasted, the day must have been shorter and shorter the farther we look back into the dim past. The day is now 24 hours, but it was once 20 hours, once 10 hours, and once 6 hours. How much farther can we go? When the 6 hours is passed, we begin to approach a limit which must at some point bound our retrospect. The shorter the day, the more is the earth bulged at the equator. The more the earth is bulged at the equator, the greater is the strain put upon the materials of the earth by the centrifugal force of its rotation. If the earth were to go too fast, it would be unable to cohere together. It would separate into pieces, just as a grindstone driven too rapidly is rent asunder with violence. Here, therefore, we discern in the remote past a barrier which stops the present argument. There is a certain critical velocity, which is the greatest that the earth could bear without risk of rupture. But the exact amount of that velocity is a question not very easy to answer. It depends on the nature of the materials of the earth. It depends upon the temperature. It depends upon the effect of pressure and on other details not accurately known to us. An estimate of the critical velocity has, however, been made, and it has been shown mathematically that the shortest period of rotation that the Earth could have without flying into pieces is about 3 or 4 hours. The doctrine of tidal evolution has thus conducted us to the conclusion that at some inconceivably remote epoch, the Earth was spinning around its axis in a period approximating to 3 or 4 hours." End quote. The existence of tides in the solid Earth as well as in the ocean was first indicated by Lord Kelvin in 1867. The first numerical estimate of the amount of the tidal oscillations of the solid Earth was made by Sir George H. Darwin in 1882 and was based on an indirect method and resulted from observation of the tides of the ocean. Further indirect methods were successfully applied later with more complete data. Sir George H. Darwin has expressed the opinion that we may now feel confident that the Earth yields to the tidal forces to the same degree as would a steel globe. The amazing accuracy of Dr. Hecker's recent observations, 1908, are marked by certain collateral considerations, among which may be mentioned the flexure of coastlines due to the varying pressure of oceanic tides and the effects of high and low barometric pressure in bending the Earth's surface. It is impossible to give an accurate measurement of the amount of the vertical motion of the Earth's surface, but it is probable that at spring tides in this latitude, the surface of the solid Earth moves up and down through about 6 inches. End of section 19.
Section 20 of The Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Fred Abood. The Science, History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy. Chapter 14. The Moon. Part 1. That the Moon is the nearest the Earth of all the heavenly bodies is one of the most obvious facts which confront the stargazer. Its regular motion must have been early appreciated by primitive man, after he had realized that the rising and setting of the sun marks regularly recurrent intervals of time. As he was able to reflect upon his observations and properly to coordinate them, he doubtless noted the connection between the form of the moon and its position in the sky with respect to the sun. For by keeping count with pebbles, or rude notches cut in a stick, he would learn that the interval of time between recurring full moons was always the same, and that the series of changes he could observe followed in regular order. Thus, when the moon appeared after sunset near the place where the sun had disappeared, he saw a thin crescent, the hollow side of which was turned away from the sun. A little later, the moon set. The next night he observed the moon, further from the sun, with a thicker crescent, and noted also that it set later, an effect that gradually increased until the semicircular disk, with the flat side turned away from the sun, was seen in rather less than a week after the first appearance of the crescent. In another week, the semicircle enlarged to a complete disk, and the moon rose about sunset and set about sunrise, being in a direction nearly opposite to that of the sun. From this time on, the size again diminished. The semicircular form was seen once more with the flat side still turned away from the sun, and toward the west instead of the east, as the moon approached the sun on the other side, rising before it and setting in the daytime. Again he saw the crescent, and marked that the time of rising approached that of sunrise, until the moon became altogether invisible. 2 or 3 nights intervened, and the new moon reappeared, whereupon the whole series of changes was repeated. In other words, this primitive man must have formulated a lunar month. All ancient records recognize this lunar month of 29.5 days, and that interval must have been adopted long before the year. By the time of Chaldean and Egyptian astronomy, however, the year was known, so that the first conception of the lunar month is lost in the mists of antiquity. The Chaldeans studied the motions of the sun and the moon. Their calendar records, which they seem to have maintained with considerable care, enabled them to discover that eclipses occurred after a period known as the Saros, consisting of 6,585 days. The nature of the moon was, of course, to them a mystery. It was known to move around the sky. The Babylonians supposed that, having a bright and a dark side, the different phases were caused by the bright sides coming more and more into view during its movement around the sky. In the 7th century, Pythagoras taught more correctly that the moon, like other heavenly bodies, was spherical, and that it was bright because it received the light of the sun. The phases, he rightly judged, were due to a greater or less amount of the illuminated half turned toward us, and the curve forming the boundary between the bright and dark portions of the moon was to him conclusive evidence of a spherical shape. He was later supported in his theory by Aristotle, who made a similar, clear and definite statement of the reason for the phases of the moon. Perhaps the first systematic study of the moon was that of Aristarchus, a famous member of the Alexandrian school, who flourished in the first half of the 3rd century and wrote a treatise on the magnitudes and distances of the sun and moon, which still survives. Taking the moon when it was half full, so that a line drawn to it from the sun made a right angle with the line from the moon to the earth, by measuring the angle between the moon and the sun, he was able to determine the ratio of the sides of this triangle and the relative distance of the moon and the sun from the earth. While the method of Aristarchus was ingenious, yet the result he obtained, that the sun was 18 to 20 times as far distant as the moon, was sadly in error, for the actual distance is nearly 400 times. Still, the difficulties in the way of accurate observation were enormous for lack of proper instruments. Aristarchus also took advantage of the solar eclipse to ascertain the distances of these two bodies, and reasoned correctly that when the moon sometimes rather more than hides the surface of the sun, and sometimes does not quite cover it, their diameters must vary as their real distances. He even obtained, by eclipse observations, a value for the diameter of the moon in terms of that of the earth. What would have been an excellent approximation was marred, however, by an incorrect estimate of the apparent size of the moon, which he took as 2 degrees instead of 1/2 a degree. Nevertheless, this work was an important advance in practical astronomy. It paved the way for Hipparchus, who discussed the motions of the moon, motions which, long before his time, were known to be irregular and much more complicated than those of the sun. The path of the moon is always changing, and its motions are subject to variation. Hipparchus notes that the part of the moon's path in which the motion is most rapid is not always in the same position on the celestial sphere, but moves continuously. He was able to realize the different motions of the moon, to distinguish the various months based upon them, and to employ the Chaldean and other early eclipse observations for determining the position of the moon at various earlier epochs. Hipparchus really evolved a most complicated set of motions. He was aware of the shortcomings of his theory, but was unable to reconstruct it in a satisfactory manner. Following out the eclipse method of Aristarchus, Hipparchus made a determination of the relation between the distances of the sun and moon, measuring their angular diameters, and found that the distance of the moon is nearly 59 times the radius of the Earth. Combining this figure for the distance of the sun with that of Aristarchus, a value of 1,200 times the radius of the Earth was obtained, which value was employed for many centuries. Ptolemy, in the 4th book of the Almagest, discusses the length of the month with the theory of the moon, and makes the important announcement of a further inequality in the moon's motion, which Hipparchus had only suspected, and which was due in large part to its position with respect to the sun. This was later termed evection, and involved a still further complication of the mathematical computations of Hipparchus, because it meant the use of an epicycle and a deferent, which was itself a moving eccentric circle, the center of which revolved around the Earth. Ptolemy's mathematics and ingenuity were able to fit his theory to observations. Although his work showed many inconsistencies which, great as he was unable to control, nevertheless it represented a notable development in astronomy. To Ptolemy is due the parallax method for obtaining the distance of the moon by observing its direction from 2 points on the Earth's surface, and by finding the distance between these 2 points in terms of the Earth's radius. This distance of the moon, he estimated, was 59 times the radius of the Earth. With this value, according to the method of Hipparchus just mentioned, he computed the distance from the Earth to the Sun. He found that the distance was 1,210 times the radius of the Earth, which value was equally in error as compared with the modern figure. The actual distance is about 20 times this amount. So readily were the motions of the moon observed, and so carefully were the records maintained, that even at an early date, much was known about its motions. These data enabled much calculation of the moon's motion to be carried on, so that early mathematical astronomy dealt with the moon in no small degree. Various irregularities of its motion and appearance were discussed, and practically all of the notable astronomers made some contributions to our knowledge of the satellite. Even an outline of these discussions would lead the reader far afield into the depths of mathematics, for which reason it is possible to mention only a few of the important researches and to indicate merely their general nature. The study of the moon had a practical importance, however, as lunar positions were early used to determine longitude in navigation, and lunar tables were calculated by government and other astronomers. Nowhere was there more interest manifested in the problem of the motion of the moon than at Greenwich Observatory, where the matter had always been a specialty of that institution. It is a curious fact, states the late Professor Newcomb in his Reminiscences of an Astronomer, that while that observatory supplied all the observations of the moon, the investigations based upon these observations were made almost entirely by foreigners, who also constructed the tables by which the moon's motion was mapped out in advance. The most perfect tables made were those of Hansen, the greatest master of mathematical astronomy during the middle of the century, whose tables of the moon were published by the British government in 1857. They were based on a few of the Greenwich observations from 1750 to 1850. The period began with 1750 because that was the earliest at which observations of any exactness were made. Only a few observations were used because Hansen, with the limited computing force at his command, only a single assistant, I believe, was not able to utilize a great number of the observations. The rapid motion of the moon, a circuit being completed in less than a month, made numerous observations necessary, while the very large deviations in the motion produced by the attraction of the sun made the problem of the mathematical theory of that motion the most complicated in astronomy. Thus it happened that, when I commenced work at the Naval Observatory in 1861, the question whether the moon exactly followed the course laid out for her by Hansen's tables was becoming of great importance. For a year or two our observations showed that the moon seemed to be falling a little behind her predicted motion. But this soon ceased, and she gradually forged ahead in a much more remarkable way. In 5 or 6 years it was evident that this was becoming permanent. She was a little farther ahead every year. What could it mean? To consider this question, I may add a word to what I have already said on the subject. In comparing the observed and predicted motion of the moon, mathematicians and astronomers, beginning with Laplace, have been perplexed by what are called inequalities of long period. For a number of years, perhaps half a century, the moon would seem to be running ahead, and then she would gradually relax her speed and fall behind. Laplace suggested possible causes, but could not prove them. Hansen, it was supposed, had straightened out the tangle by showing that the action of Venus produced a swinging of this sort in the moon. For 130 years, she would be running ahead, and then for 130 years, more falling back again, like a pendulum. 2 motions of this sort were combined together. They were claimed to explain the whole difficulty. The moon, having followed Hansen's theory for 100 years, would not be likely to deviate from it. Now it was deviating. What could it mean? Taking it for granted, on Hansen's authority, that his tables represented the motions of the moon perfectly since 1750, there was no possibility of learning anything from observations before that date. As I have already said, the published observations with the usual instruments were not of that refined character which would decide a question like this. But observations of stars, which might be available, and which had been made in many instances, would have an important bearing on this work. For if an oscillation or passage of the moon between a star and the earth occurred, and its time registered, the path of the moon in the heavens and the time at which it arrives at each point of the path would be determined if the time of the oscillation was known within 1 or 2 seconds. Professor Newcomb continues, "It was not until after the middle of the century, 17th, when the telescope had been made part of astronomical instruments for finding the altitude of a heavenly body, and after the pendulum clock had been invented by Huygens, that the time of an oscillation could be fixed with the required exactness. Thus it happens that from 1640 to 1670, somewhat coarse observations of the kind are available, and after the latter epoch, those made by the French astronomers became almost equal to the modern ones in precision. The question that occurred to me was, is it not possible that such observations were made by astronomers long before 1750? Searching the published memoirs of the French Academy of Sciences and the Philosophical Transactions, I found that a few such observations were actually made between 1660 and 1700, I computed and reduced a few of them, finding with surprise that Hansen's tables were evidently much in error at that time. But neither the cause, amount, or nature of the error could be well determined without more observations than these. Was it not possible that these astronomers had made more than they had published? The hope that material of this sort existed was encouraged by the discovery at the Pulkowa Observatory of an old manuscript by the French astronomer Delisle, containing some observations of this kind. I therefore planned a thorough search of the old records in Europe to see what could be learned. By good fortune, suitable observations were found at the Paris Observatory, and their relations and the method of making were studied, and everything necessary was copied. This work took some 6 weeks, but Professor Newcomb says, "The material I carried away proved the greatest find I ever made." 3 or 4 years were spent in making all the calculations I have described. Then it was found that 75 years were added, at a single step, to the period during which the history of the moon's motion could be written. Previously, this history was supposed to commence with the observations of Bradley at Greenwich, about 1750. Now it was extended back to 1675, and with a less degree of accuracy, 30 years farther still. Hansen's tables were found to deviate from the truth in 1675, and subsequent years to a surprising extent, but the cause of the deviation is not entirely unfolded, even now. One curious result of this work is that the longitude of the moon may now be said to be known with greater accuracy through the last quarter of the 17th century than during the 90 years from 1750 to 1840. The reason is that, for this more modern period, no effective comparison has been made between observations and Hansen's tables. End of section 20. Section 21 of The Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Fred Abood. The Science, History of the Universe, Volume 1. Edited by Francis Rolt Wheeler. Astronomy. Chapter 14. The Moon. Part 2. As the Moon rotates around the Earth, while the Earth is passing in its orbit about the Sun, it will be obvious that twice in its journey the Sun must come into a line of intersection of the Moon's orbit with that of the Earth. When this happens at the time of full moon, the Earth will lie directly between the Moon and the Sun, so that the light from the Sun is intercepted and a shadow is formed on the Moon's surface. Sometimes the Moon only partially enters the Earth's shadow, and then the eclipse, as this phenomenon is termed, is partial. If, however, the Sun is situated on the line of intersection at the time of new moon, then the Sun will be eclipsed, and a solar eclipse so rich in astronomical significance occurs. Solar eclipses have been discussed elsewhere, and their importance explained. Lunar eclipses, besides enabling us to check the motions of the Moon and furnishing an interesting spectacle, afford little scientific information. When the black shadow on the Moon is first detected in the case of a total lunar eclipse, it is interesting to watch its encroachment until the entire surface of the satellite is covered. Even the Moon, on which no direct sunlight can fall, is often visible, glowing with a copper-colored hue, sufficiently bright to enable several of the markings on the surface to be seen. This is due to refraction of the atmosphere, which bends the sunbeams that have just grazed the Earth and permits them to fall within the shadow. In their journey through the denser atmosphere, they have become rich in red rays, which gives to the disk a ruddy or copper-like hue, analogous to that of the sun at sunrise or sunset. Whether the eclipse of the moon is total or partial depends on the extent to which it passes into the shadow of the Earth, as the accompanying diagram will indicate clearly. Lunar eclipses are useful to the astronomer for determining the length of the synodic month, and also for determining the temperature to which the moon has been raised, for when it enters the shadow, all direct light from the sun is cut off and the moon becomes cold very rapidly. Furthermore, the position of the moon with respect to the stars can be determined on such occasions with great accuracy. Like solar eclipses, eclipses of the moon can be predicted with high precision, and they are regularly announced in almanacs and ephemerides. The moon always presents the same face to the Earth, a phenomenon discovered by Galileo. It must follow that the moon rotates on its axis once in the same number of seconds that it requires for a revolution around our planet. This is explained by the fact that tides on the moon, as in the case of the Earth, have lengthened the period of rotation by their braking action. At a time when the moon was still a hot, semi-molten mass, the attraction of the Earth produced great tides, not tides of water, but tides of molten rock. These tides on the moon checked its rotational velocity and eventually constrained the moon to rotate on its axis in precisely the same period as that which it requires to revolve around the Earth. All this happened eons ago. There is no longer evidence of any tidal action because the moon is frozen. Although there can hardly be tides on the moon, yet there may be tides in the moon. It may be that the interior of the moon is still hot enough to retain an appreciable degree of fluidity, writes Sir Robert Ball. And if so, the tidal control would still retain the moon in its grip. But the time will probably come, if it have not come already, when the moon will be cold to the center, cold as the temperature of space. If the materials of the moon were what a mathematician would call absolutely rigid, there can be no doubt that the tides could no longer exist, and the moon would be emancipated from tidal control. It seems impossible to predict how far the moon can ever conform to the circumstances of a rigid body, but it may be conceivable that at some future time the tidal control shall have practically ceased. There would then be no longer any necessary identity between the period of rotation and that of revolution. A gleam of hope is thus projected over the astronomy of the distant future. We know that the time of revolution of the moon is increasing, and so long as the tidal governor could act, the time of rotation must increase sympathetically. There will then be nothing to prevent the rotation remaining as at present, while the period of revolution is increasing. The privilege of seeing the other side of the moon, which has been withheld from all previous astronomers, may, thus in the distant future, be granted to their successors. While study of the moon and its motions continued, a beginning was made in the Renaissance to examine the surface of this satellite. Leonardo da Vinci, 1452 to 1519, was the first to explain correctly the dim illumination seen over the rest of the surface of the moon when the bright part was only a thin crescent. This he maintained is due to the earthshine, or slight illumination of the moon by light reflected from the earth, just as moonshine is able to illuminate the earth. Galileo's lunar observations through his telescope were epoch-making. Not only was he able to disprove many common conceptions of the nature of the satellite and its surface, but also to present a mass of evidence of a positive character. In spite of the familiar dark markings, the Moon was really supposed to be a smooth sphere. After the introduction of the telescope, however, it was recognized by Galileo that the surface of the Earth's satellite was dotted with various inequalities, which he assumed to be mountains, valleys, and seas. Thus he correctly accounted, in part at least, for the unevenness of the surface. He was not content with mere observation of the features of the Moon's surface, but measured the height of some of the more conspicuous lunar mountains, and obtained for them an estimated elevation of 4 miles, a figure which agrees fairly well with modern estimates. Having seen and measured mountains on the Moon's surface, it seemed natural that there should be water. The large dark spots he erroneously regarded as seas, although he was not responsible for the corresponding names applied to these supposed expanses of water by some of his successors, and still preserved in lunar maps. The chief marks of astronomical progress, as revealed by Galileo's observation of the Moon, were that it was a body in many respects similar to the Earth, that it was not a perfect sphere, and that there is no fundamental difference between celestial bodies and our own Earth, either in their motions or in their general nature, which was important in the final establishment of the Copernican theory. One other discovery of Galileo's in connection with the Moon is of great importance. It had been known for many years that as the Moon revolved around the Earth, the same markings were constantly seen. With the telescope, these markings could be studied so much more distinctly that it occurred to Galileo to ascertain whether there was any change in the Moon's disk, or whether its appearance was always exactly the same. He found that as the Moon moves in its orbit around the Earth, that slight changes are seen in its appearance. In other words, small portions of the hemisphere alternately on its northern and southern half are exposed. The simplest of the motions of the Moon in this way subsequently came to be known as librations. Kepler, in his epitome of the Copernican astronomy, demonstrated that his planetary laws applied to the motion of the Moon around the Earth, despite irregularities which introduced enormous complications. In this work, however, he devotes much attention to the theory of the Moon, explaining in considerable detail both evection and variation. Galileo established the fact that the Moon was similar to the Earth in many respects. The analogy was carried somewhat further by certain of the pioneer workers with large telescopes. Even Herschel held that because the Moon closely resembled the Earth, it might be a suitable habitat for human beings. The dark spots once taken for seas and bearing that name on lunar maps are, in reality, lava, while the craters which dot the surface of the satellite, with one or two possible exceptions, belong to volcanoes long since extinct. The dark lines once known as rills, which it was assumed were rivers, are plainly without water. If there is a lunar atmosphere, its density must be very small, in fact less than that of the atmosphere far above the Earth. That there is a very rare lunar atmosphere seems to be probable. In fact, the assumption of an atmosphere is necessary for the explanation of certain phenomena. After Galileo's lunar studies, the next important work was that of John Hevel of Danzig, 1611 to 1687, who published in 1647 his Selenographia, in which not only the text, but the plates were prepared by him. Here he systematically describes the names and chief features of the Moon, the immense craters and seas, employing many names taken from the Earth, such as Apennines, Alps, and Mare Serenitatis for the Pacific Ocean, all designations still found on modern lunar maps. Not all of his names have survived. John Baptiste Riccioli, 1598 to 1671, in a treatise on astronomy called The New Almagest, 1651, gave to various mountains and craters the names of distinguished men of science and philosophers. Hence the names of Plato, Archimedes, Tycho, and Copernicus are found on lunar maps. These names have survived in considerable number. More modern map makers, such as Beer and Maedler, whose map was published in 1837, and Schmidt of Athens, who published a map of the moon 7 feet in diameter in 1878, have carried out this idea. Modern astronomers are likewise honored, with the names of various points represented on the maps. For the origin of the moon, the mind must be forced to look back millions and millions of years to a time when our Earth existed in a very different form. Then it was not a solid mass, but a globe of molten material on which floated a crust, perhaps some 35 miles thick. It rotated not in a period of 24 hours, the present day's length, but at a terrific velocity which may have made the day some 3 hours in length. Such a speed of revolution naturally produced a most powerful centrifugal force. One day a cataclysm occurred. 5,000 cubic millions of miles of matter were thrown off into space. Thus the moon was born. A great scar was left on the surface of the Earth, a scar which, in the opinion of Professor William H. Pickering, is the basin of the Pacific Ocean. After this rending of the Earth, the remaining parts of the crust, afloat on the liquid interior, were split along irregular lines into two pieces, which drifted apart and were filled by the waters of the Atlantic and Pacific Oceans. This theory of Pickering's is diametrically opposed to that of Professor T.J.J.C., who claims that the moon is in reality a planet captured by the Earth in its wanderings through space, and that all satellites have been thus captured. Whatever the origin of the moon, it is the largest of all the planetary satellites, yet smaller in mass than the Earth, from which it is separated by a distance that varies between 222,000 and 253,000 miles. Its gravity is equal to about 1/6 that of the Earth, for which reason the same amount of energy acting, for example, in a volcanic upheaval, produced mountains higher than those on the Earth. This mass of the moon is about 1/80th that of the Earth, or 73 trillion tons. The accompanying diagram shows the comparative size of the Earth and the moon. The diameter of our planet is 7,914 miles, while that of the moon is 2,160 miles, so that the diameters stand very nearly in the relation of 4:1, while the superficial area of the moon is equal to about 1/13th part of the surface of the Earth. The average distance of the moon from the Earth is also fairly constant, and the average fluctuations do not exceed more than about 13,000 miles on either side of its mean value of 239,000 miles. The moon is essentially a dead planet in the eyes of most astronomers. Its fires long since have been extinguished. It is a great globe of chilled slag. Its craters have no counterpart on the Earth. The lunar crater is a great circular plain, 50 or even 100 miles in diameter, around which rises a precipice perhaps 5 or 10,000 feet, while in the center there may be a hill or two about half as high. Thousands of these volcanoes are visible in the telescope. How these craters were formed is a puzzle. Some astronomers hold that they mark the impact of countless meteorites. Others assume them to be the product of gigantic bubbles in a once molten mass that burst. Again, it is claimed that they are volcanoes resembling those of the Earth. Most astronomers tell us that the craters have long been dead, that the Moon has had for centuries no atmosphere, and therefore cannot have water or support plant or animal life. Professor William H. Pickering, however, tells us of an exceedingly rare lunar atmosphere and maintains that the Moon's craters are not all extinct. He even claims that certain great white expanses are snow and ice, and furthermore, that there is evidence of the growth and decay of vegetation. To support his views of vanishingly feeble volcanic activity, he calls attention to the little crater named Linne, after the famous naturalist Linnaeus. In modern times, this crater has unquestionably undergone changes. Only a few centuries ago, it was described on the old maps as a crater of moderate size, and later as a very small, round, brilliant spot. A dead volcano cannot alter its shape. If there are still a few intermittently active volcanoes, they must expel water and carbonic acid gas, judging by earthly volcanoes. But water cannot be found on the Moon as a liquid, for the temperature of its surface is probably not far from 460 degrees Fahrenheit below zero. Many of the elevated peaks are capped with a silver glow, which also characterizes the lining of the craterlets. In Pickering's eyes, that white sheen is snow. He believes also in accumulations of snow and ice at the poles. If carbonic acid is expelled by lunar volcanoes, it must cling to the Moon with great tenacity because of its weight. Since it is the food of plant life, it may possibly support vegetation on the Moon. Professor Pickering sees in variable dark spots on the planet organic life resembling vegetation. He figures that since certain lichens grow in certain regions of the Earth where the temperature never rises above the freezing point, there is no reason why that vegetation may not flourish on the Moon's surface. End of section 21.
Section 22 of the Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 1. Edited by Francis Rolt Wheeler. Astronomy. Chapter 15. Mars, Part 1. Mars is another instance of a celestial body whose discovery long antedates written history, for which reason it is natural to assume that its appearance in the heavens and its motions have always been known to mankind. Its ruddy light naturally associated it in the Greek mind with the god of war, just as the soft, warm glow of Venus was considered appropriate to the goddess of love. To the Chaldean and other ancient stargazers, the motions of the planet were indeed of interest. No planet has received greater attention from astronomers, or has been used more for the solution of important astronomical and cosmical problems. Thus, it was from the observation of the passage of the Moon in front of Mars, or what is termed by astronomers an occultation of the planet, that Aristotle concluded that the planets were more distant than the Sun and Moon. What reason he had for including the Sun is difficult to conceive, as an occultation of that body would be quite impossible. Later, it was from the study of the motions of the planet made for Tycho Brahe that Kepler was able to derive his great laws of planetary motion. By observing the great hourglass sea, or Syrtis Major, on Mars, Huygens, in 1659, noted the rotation of the planet on its axis, and from a measurement of the planet made its opposition Riker was able to obtain a reasonably accurate estimate of the distance of the Sun in 1673. 1783, Herschel had written, "The analogy between Mars and the Earth is perhaps by far the greatest in the whole solar system." For over a century, the development of this analogy has been one of the most important features of astronomy, especially in popular estimation. Today, with a wealth of scientific and observational data acquired during the last score of years, the question, although more fully and intelligently discussed, is as far from solution as ever. Mars revolves around the Sun in an orbit whose mean distance is 141,500,000 miles. But this orbit is so eccentric, amounting to 0.093, that the distance varies about 13 million miles. As this distance from the Sun is about 1/2 as far again as that of the Earth, the light and heat that Mars receives are only about 4/9 of the light and heat received by the Earth, an important consideration in discussing the possibility of life on its surface. The real diameter of Mars is about 4,200 miles, a figure correct within 20 miles, so that its surface is 23/100ths and its volume is 0.147 or 1/7 that of Earth. The mass of the planet, derived from observation of its satellites, is about 1/9.4 that of the Earth, so that its density is 0.73 and the attraction of gravity on its surface is 0.38 that of Earth. Mars reflects 0.26 of the light that it receives, which is just double that of Mercury. In Mars may be seen a striking difference between the superior and inferior planets, for the crescent phases of the latter are conspicuously absent. This is because the orbits of Mars and the other superior planets lie outside that of Earth. Consequently, such a planet never comes between the Earth and the Sun. At quadrature, a certain amount of the unilluminated portion is turned towards the Earth, so that the planet appears like a moon 3 or 4 days from full, with a distinctly gibbous appearance. Kepler suspected the existence of satellites from a somewhat cryptic utterance of Galileo's in regard to the triple Saturn. No particularly sound reasons were advanced for the existence of such satellites. Still, that they might be found is forcibly reflected in 18th century literature. In Gulliver's Travels, 1726, is the striking statement that an astronomer on the floating island of Laputa had discovered 2 tiny satellites of Mars. Dean Swift even advanced the extraordinary statement that one of these moons revolved around the planet in 10 hours, the approximate correctness of which will presently be apparent. Furthermore, Voltaire, in his Micromegas, published in 1752, and obviously modeled on Gulliver's Travels, also speaks to these small bodies. Although literature and imagination had preceded observation, astronomers could not detect any companions to the ruddy planet until August 11, 1877, when Professor Asaph Hall, using the 26-inch refractor of the U.S. Naval Observatory at Washington, which at the time of its construction in 1873 was the largest telescope in the world, studied the vicinity of Mars with unusual care. In 1877, it was at conjunction, so that conditions were favorable for an exhaustive inquiry. On August the 11th, Professor Hall detected a minute speck of light near the planet, and a few days later, August 16th, he ascertained positively that it was a satellite. On the following evening, a second body was discovered, bewilderingly rapid in its motion. Since that time, the 2 satellites have frequently observed at opposition, even with much smaller instruments. On July 18, 1888, the Large Lick telescope was able to reveal them with their brightness was about 1/8 at the time of their discovery. The names appropriately designated to the new satellites, Deimos and Phobos, fear and panic, were taken from the Iliad and represent the companions in the battle of the god of war. The satellites are very small, having diameters respectively of 6 and 7 miles, as photometrically measured at Harvard University soon after their discovery by Professor Pickering. Phobos, the inner, is larger and travels an elliptical orbit in 7 hours, 39 minutes, and 22 seconds at a distance of only 3,760 miles. Deimos, its companion, moves in a nearly circular orbit in 30 hours, 18 minutes, at a distance from the planet of 12,500 miles. It should be remembered in all discussions of the nature of the surface of the planet Mars and in developing theories based therein that astronomers must deal with the little disk which 1 every 15 years has a maximum of about 1/5000th the area of the full moon. When the nearest Earth-Mars is at a distance of 35,500,000 miles and when observed by a telescope magnifying 1,000 times, it appears as only large as the moon with an ordinary field glass, enlarging 6 or 7 times. In other words, Mars is brought to its distance of 35,500 miles. Hence it is difficult to distinguish minute details. Consequently, visual and photographic observation of Mars must be of the most refined character, for especially in the former, there is opportunity for psychological or subjective phenomena to occur in connection with the observation. While it is neither rational nor scientific to deny what credible observers claim they have seen through the telescope in examining the planet, yet it must be recognized that visual observations are attended by necessary limitations and should be received in a spirit of caution rather than of enthusiasm. The mapping of Mars is no recent matter, for even in 1659 a rough sketch of the surface of the planet was made by Huygens, in which the V-shaped marking at the equator pointing to the north can be identified as the Syrtis Major. This was followed by rough sketches from time to time down to 1840, when Mädler first began a systematic charting of the planet. His map was followed in 1864 by Quasars, by Flammarions in 1876, and Green's in 1877. Drawings of various parts of the planet were made during these intervals, but were not combined into good charts. Observations made by Professor Lowell and his staff at the observatory in Flagstaff, Arizona, have had the study of this planet especially in view. The Lowell Observatory itself is situated 7,300 feet above the sea and contains an excellent 24-inch telescope, with which it is claimed that the faintest stars shown on the chart made at the Lick Observatory with its 36 instrument are perfectly visible. The atmosphere is well adapted for telescopic work, so that Professor Lowell and his colleagues possess singular advantages over other observers. On the other hand, in many important respects, there has been a lack of corroboration of their observations. The surface of Mars, as seen in the telescope, is composed of 2 white polar caps which wane with the approach of summer, orange areas, which are supposed by Lowell and his followers to be deserts, and blue-green areas which change their hue to orange during the Martian autumn and winter and reassume their verdant tint in the spring. The planet is covered with a network of fine lines first discovered by Schiaparelli in 1877 and called by him canals, a designation by which they are still known. These canals connect the polar ice caps with the temperate and equatorial zones. According to Professor Lowell, they may be regarded as planetary irrigation ditches, which serve the purpose of leading the melting water of the poles to those desert regions which would still blossom if properly watered. The canals disappear with the approach of winter and creep down from the poles towards the equator in the summer, a phenomenon which long puzzled astronomers until Pickering ingeniously suggested that we see not the canals themselves, for they are much too narrow, but the vegetation which fringes their banks, which withers as the cold of winter descends, and which flourishes with the melting of the snows. It was Schiaparelli who also first announced the curious doubling of the canals in certain instances, an announcement which was at first received with derision, but which has since been confirmed by his disciple, Lowell, and the astronomers of the great observatories. This curious gemination has not been satisfactorily explained, although Professor Lowell attributes it part to vegetal causes. By opponents of his theory, the doubling is regarded as an optical illusion, which can hardly be the case because all and not certain of the canals would exhibit the phenomenon. Furthermore, there is some photographic evidence offered by Mr. Lampland of Professor Lowell's staff that both the canals and their doubling are real. End of section 22.
Section 23 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Nagami. The Science History of the Universe, Volume 1. Edited by Francis Rolt Wheeler. Astronomy. Chapter 15, Part 2. Mars. The visual observations of Professor Lowell have been undertaken with great thoroughness and have brought to light such material which he has employed in the development of his theories. To do justice to his work in a single chapter is manifestly impossible. It will be most satisfactory to the reader to recapitulate in Professor Lowell's own words, derived from his work on Mars and its canals, the fundamental facts which he has recorded and on which he bases his conclusions. They are as follows, quote, Number 1. Mars turns on its axis in 24 hours, 37 minutes, 22.65 seconds with reference to the stars, and in 24 hours, 39 minutes, 35 seconds as a mean with regard to the Sun. Its day, therefore, is only about 40 minutes longer than ours. Number 2. Its axis is tilted to the plane of its orbit by about 23 degrees 59 minutes. Most recent determinations of 1905. This gives the planet's seasons almost the counterpart of our own in character, but in length nearly double ours. For number 3, its year consists of 687 of our days, 669 of its own. Number 4, polar caps are plainly visible, which melt in the Martian summer to form again in the Martian winter, thus implying the presence of a substance deposited by cold. Number 5, as the polar caps melt, they are bordered by a blue belt, which retreats with them. This excludes the possibility of their being formed of carbon dioxide, and shows that of all the substances we know, the material composing them must be water. Number 6, in the case of the southern cap, the blue belt has widenings in it in places. These occur where the blue-green areas bordering upon the polar cap are largest. Number 7, the extensive shrinkage of the polar snows shows their quality to be inconsiderable and points to scanty deposition due to dearth of water. Number 8, the melting takes place locally after the same general order and method, Martian year after year, both in the south cap. Number 9, and in the north one. This is evidenced by the recurrence of rifts in the same places annually in each. The water thus let loose can therefore be locally counted on. Number 10, that the south polar cap is given to greater extremes than the north one implies again, in view of the eccentricity of the orbit and the tilt of the axis, that deposition in both caps is light. Number 11, the polar seas at the edges of the caps being temporary affairs, the water from them must be fresh. Number 12, the melting of the caps on the one hand and their reforming on the other affirm the presence of water vapor in the Martian atmosphere of whatever else that air consists. Number 13, since water vapor is present, of which the molecular weight is 18, it follows from the kinetic theory of gases that nitrogen, oxygen, and carbonic acid of molecular weights 28, 32, and 38 respectively are probably there too, owing to being heavier. Number 14, the limb light bears testimony to this atmosphere. 15, the planet's low albedo points to a density for the atmosphere very much less than our own. Number 16, the apparent evidence of a twilight goes to affirm this. Number 17, permanent markings show upon the disk, proving that the surface itself is visible. Number 18, outside of the polar cap, the surface is divided into red ochre and blue-green regions. The red ochre stretches have the same appearance as our deserts seen from afar. Number 19, and behave as such, being but little affected by change. Number 20, the blue-green areas were once thought to be seas, but they cannot be such because they change in tint according to the Martian season, and the area and the amount of the lightning is not offset at the time by corresponding darkening elsewhere. Number 21, nor by any augmentation of the other polar cap or precipitation into cloud. It cannot, therefore, be due to shifts of substance. Number 22, furthermore, They are all seamed by lines and spots darker than themselves, which are permanent in place so that there can be no bodies of water on the planet. Number 23. On the other hand, their color, blue-green, is that of vegetation. This regularly fades out, as vegetation would, to ochre for the most part, but in places changes to a chocolate brown. Number 24. The change that comes over them is seasonal in period, as that of vegetation would be. Number 25. Each hemisphere undergoes this metamorphosis in turn. Number 26. That it is recurrent is again proof positive of an atmosphere. Number 27. The changes are metabolic, since those in one direction are later reversed to a restoration of the original status. Anabolic as well as catabolic processes thus go on there. That is, growth as well as decay takes place. This proves them of vegetal origin. Number 28. The existence of vegetation shows that carbonic acid, oxygen, and undoubtedly nitrogen are present in the Martian atmosphere, since plants give out oxygen and take in carbonic acid. Number 29. The changes in the dark areas follow upon the melting of the polar caps, not occurring until after that melting is underway. Number 30. And not immediately then, but only after the lapse of a certain time. Number 31. Though not seas now, from their look, the dark areas suggest old sea bottoms, and when on the terminator appear as depressions, whether because really at a lower level or because of less illumination is not certain. Number 32. That they are now the parts of the planet to support vegetation hints the same past office, as water would naturally drain into them. That such a metamorphosis should occur with planetary aging is in keeping with the kinetic theory of gases. Number 33. Terminator observations prove conclusively that there are no mountains on Mars, but that the surface is surprisingly flat. Number 34. But they do reveal clouds, which are usually rare and are often, if not always, dust storms. Number 35. White spots are occasionally visible, lasting unchanged for weeks in the tropic and temperate regions, showing that the climate is apparently cold. Number 36. But at the same time proving that most of the surface has a temperature above the freezing point. Number 37. In winter, the temperate zones are more or less covered by a whitish veil, which may be hoarfrost or may be cloud. Number 38. A spring haze surrounds the North Polar Cap during the weeks that follow its most extensive melting. Number 39. Otherwise, the Martian sky is perfectly clear, like that of a dry desert land. End quote. These facts, according to Professor Lowell, make reasonably evident on Mars the presence of, quote, number 1, days and seasons substantially like our own. Number 2, an atmosphere containing water vapor, carbonic acid, and oxygen. Number 3, water in great scarcity. Number 4, a temperature colder than ours, but above the Fahrenheit freezing point, except in winter and in the extreme polar regions. Number 5, vegetation. End quote. While all of Professor Lowell's observations and results are not accepted by all astronomers, and there is considerable opposition to his conclusions, nevertheless, they are of interest and worth stating as representing this aspect of the matter in his own words. Comparative studies of lunar and Martian spectra made on the summit of Mount Whitney in September 1909 by Campbell of the Lick Observatory seemed to preclude the possibility of much water on Mars. Campbell's photographs show that the Martian atmosphere is no richer in water than the Moon's, which, if true, summarily disposes of Martian life. Slipher of Lowell's staff claims to have obtained ample spectroscopic evidence of water. The following paragraphs, taken from the concluding chapter of Lowell's book on Mars and its canals, may be said fairly to sum up his views on Martian life. Quote, that Mars is inhabited by beings of some sort or other, we may consider as certain as it is uncertain what these beings may be. The theory of the existence of intelligent life on Mars may be likened to the atomic theory in chemistry, in that in both we are led to the belief in units which we are alike unable to define. Both theories explain the facts in their respective fields, and are the only theories that do, while as to what an atom may resemble we know as little as what a Martian may be like. But the behavior of chemic compounds points to the existence of atoms too small for us to see, and in the same way, the aspect and behavior of the Martian markings implies the action of agents too far away to be made out. One of the things that makes Mars of such transcendent interest to man is the foresight it affords of the course earthly revolution is to pursue. On our own world, we are able to study only our present and our past. In Mars, we are able to glimpse in some sort our future. Different as the course of life on the two planets undoubtedly has been, the one helps, however imperfectly, to better understanding of the other." End quote. The views expressed by Professor Lowell in the work just quoted were further developed by him in the course of a few years succeeding its publication, and in Mars as the Abode of Life, published in 1908, he expresses himself even more firmly convinced that Mars is inhabited by a race of intelligent beings. Additional study of Martian phenomena, according to Professor Lowell, indicates that the canals and oases, as he sees them, are proof that life of no mean order of intelligence prevails on the planet. He suggests, quote, "Part and parcel of this information is the order of intelligence involved in the beings thus disclosed. Peculiarly impressive is the thought that life on another world should thus have made its presence known by its exercise of mind. That intelligence should thus mutely communicate its existence to us across the far stretches of space, itself remaining hid, appeals to all that is highest and most far-reaching in man himself. More satisfactory than strange this, for in no other way could the habitation of the planet have been revealed. It simply shows again the supremacy of mind. Men live after they are dead by what they have written while they are alive, and the inhabitants of a planet tell of themselves across space, as do individuals athwart time, by the same imprinting of their mind." End quote. To this he adds the statement that conditions for life on the planet are approaching an end, as it is rapidly drying up, and that the energies of the inhabitants are being the slowly diminishing supply of water. Quote, "The drying up of the planet is certain to proceed until its surface can support no life at all." End quote. So that as compared with the Earth, Mars presents a distinctly later period of evolution. No such danger at present confronts our own planet, but assuming that these explanations are correct, it is not improbable that the cooperative action of all the nations of the world may be required at some future date to deal with a similar problem. In opposing the idea of canals on the surface of Mars, much stress has been laid on the alleged fact that the finer markings and some of the apparent doublings are based upon optical illusions or psychological phenomena. Thus, to prove that instinctively the eye would arrange in the form of straight lines vague suggestions of markings, E.W. Maunder of the Greenwich Observatory, England, and J.E. Evans of the Royal Hospital School at Greenwich in 1902 performed an experiment with a number of schoolboys. A circular disc was exhibited 5 or 6 inches in diameter, on which were represented with some accuracy the shaded area of the planet as it might appear in the telescope. Instead of canals, a few faint wavy lines and a larger number of faint dots were inserted promiscuously. The boys were told to fill in with pencil on small circles on sheets of paper the details of the object exhibited to them, exercising as much care as possible. The object of the experiment was not communicated to the boys. None of them had any idea of the nature of the planet's surface. The result was that boys at the greatest distance from the object where the faint lines and dots were just beyond the limits of separate visibility, drew canals remarkably like those noted by the telescopic observers of the planet. Hence, it was supposed that the eye in some way integrated such faint stimuli as irregular scattered dots and faint wavy lines into straight lines which have no objective existence. Much has been made of this test, but it may hardly be called conclusive, for Flammarion, when repeating the experiment with French boys, was unable to secure in their sketches lines resembling canals. Moreover, photographs taken during the opposition of 1905 at Flagstaff bring out a large number of the more prominent canals as straight lines. It is possible that psychology plays an important part, and Professor Andrew Ellicott Douglas of the University of Arizona, who has had opportunities to observe the planet at several favorable oppositions, believes the subjective phenomena have much to do with Martian observations. He says, quote, "One may confidently say that such realities do exist, but with the very faint canals, whose numbers reach occasionally well into the hundreds, discordance reigns supreme, and it is frequently found that different drawings by the same artist antagonize each other across the page. Considerations along these lines led me to study seriously the origin of these inconsistent faint canals by the methods of experimental psychology, and the application of these methods has resulted in a new optical illusion and new adaptations of old and well-known phenomena." End quote. The most important of these phenomena was the halo effect, where secondary images are produced under unusual conditions, which images affect the minute details of the surface. Professor Douglas also found that the irregular refraction of the eye produced apparent rays as from a small spot, which could be obviated in part by changing the position of the observer's head. Quote, "The ray illusion," he says, "is to me a very satisfactory explanation of many faint canals radiating from those small spots on Mars called lakes or oases. The only objective reality in such cases is the spot from which they start." End quote. Referring again to the halo, he reaches the conclusion that, quote, "The halo with its light area and secondary images accounts for details which have no objective reality, such as bright limbs of definite width, canals paralleling the limb or dark areas, numerous light margins along dark areas and light areas in the midst of dark, abundantly exemplified in Schiaparelli's map of 1881 and 1882. Professor Lowell, it must be said, has the unique advantage, or misfortune it may be, to see canal-like markings that are not visible to other astronomers. Thus on Venus he saw bands or lines which he considered bore a superficial resemblance to the canals of Mars and were apparently permanent and not due to clouds. Again, he claims to have seen lines resembling canals on the third satellite of Jupiter, which others have failed to recognize. Hence, many astronomers believe that he is predisposed to see such phenomena. Furthermore, canal-like appearances have been noted on the surface of the Moon by Professor W. H. Pickering as radiating from the central peaks of the northwestern slopes of the central mountain range of the crater of Eratosthenes. He observed two canals which in a small telescope appear straight, yet when seen with a large glass present considerable irregularity of structure. Other and new branches or canals were also seen. In various parts of the same crater, but especially in the southeastern and northern portions, numerous small canals and lakes present themselves. These markings are practically identical in appearance with those seen upon the planet Mars. They are too small to be well shown on photographs and seem to be of much more regular structure than the larger markings, which are also called canals. It is possible that this difference is due merely to the fact that the larger markings are better seen. There can be no free water on the Moon's surface, hence any canals with flowing water are quite out of the question. Yet the appearance is vouched for as remarkably similar to that on Mars by an observer who knows the surfaces of both bodies. End of section 23.